Okay, let's get started. Welcome to the PufferLib 1.0 launch. This is a project, not a product. It's all open source. Project I'm fully excited to bring to you guys. I've been working on this for a while, at least full-time since I graduated. And this is something that I really think is going to change the way that we look at reinforcement learning. Not going to be anything big or flashy, really just a small set of low-level tools, but it's going to make a big difference in how easy it is to just do work in reinforcement learning. I want to keep this preamble short. Today is not about talking heads. It's about a bunch of quick tech demos and showing what this stuff can do. So the only things I'm going to start with are where you can get all of these demos and run them yourselves, as well as what I'm running them on. So what you see right here with the little pufferfish prompt, this is PufferTank. It is a container. We ship pre-built images with a good version of PyTorch and Python, plus all the annoying to install dependencies. Not for PufferLib. PufferLib doesn't have any, but for all of the environments that I'm going to be using. It makes it a lot easier. We've got like a little hook, so if you use VS Code, it's super easy. As you can see, I'm not doing that. It's also very easy just in a console. So if you see, I'm in this PufferTank folder right now. You can get this on GitHub/PufferAI/PufferTank. Container's a little bit beefy, but that's just right PyTorch and Python. Ready? Second, just muting extra mics on the Zoom call. Okay. You can get this right here, PufferAI PufferTank, and you can also get it on Docker Hub, PufferAI/PufferTank tag 1.0. Starts up the container, and then the box that I'm running this on, I'm SSH'd into a desktop. This is a 13900K with a single 4090. So it's a nice desktop, but it's a desktop. No H100s, no A100s, nothing. So the first thing that I'm going to do is I'm going to start in PufferLib, which is included, run some of the examples. I'm going to start with really the thing that motivated PufferLib and the solution that I found to it. And then you're going to see how this one very small wrapper is going to make everything so much easier. So this is CleanRL's PPO Atari. I see we have Costa in the chat on YouTube. Amazing, amazing project. So I'm using it to improve over because it's the best thing, not to like smash it as a baseline. 2,800 or so steps per second, a little close to 3,000. And then the difference between this script and vanilla, so the original, all I did was I added multiprocessing vectorization from Gymnasium, just so that it would use multiple cores, and then I fixed an unnecessary copy. And just so you can see that I did actually improve it, so that we're using a stronger baseline, not a weaker one. The original is between 1,200 and 1,500 steps per second, depending on the temperature where this desktop is. It is currently in Florida. So what happens now if we want to run this same sort of a script, this same PPO, on a more complex, interesting environment like NetHack, or we'll use MiniHack for this? Well, we shouldn't have to change very much. This is how you would think that you would. You're going to get rid of all these Atari wrapper imports, add the MiniHack ones, change the env string, set a reasonable batch size, get rid of all these junk Atari wrappers, add some MiniHack stuff, It just needs a compatibility wrapper for the latest version of Gymnasium. And then we're going to add in a MiniHack network. So the only other changes I have other than this are moving a couple lines down a little bit for demonstration purposes and changing the data type to match MiniHack. So assuming that you already have a network suitable for MiniHack, this is 5, maybe 10 minutes of work. Unfortunately, this is not going to work. We have the error right here, which is line 191. And we can see that CleanRL is allocating a big tensor for observations. This works fine for Atari and many simpler environments that just have flat observations like this. But many of the more complex and interesting ones have structured observations. Some of them even have structured actions. So that means that in order to actually use CleanRL for something like MiniHack, you're going to have to modify this obs to be a big dictionary with a whole bunch of different types, a whole bunch of different shapes and data. And then anywhere that you use obs, you're going to have to make the appropriate changes. So you're not going to be able to just .CUDA these here because it's a dictionary. TensorDict and other stuff help with this, but still, you're going to have to do some extra work. Here, you're not going to be able to do this because it's a dictionary. Down here as well. Pretty much anywhere you use obs, you're going to add a whole bunch of extra logic. Now, sure, this is just like a little bit of engineering, but I can tell you from experience, and anybody else who's worked with these more complex environments can tell you that this is just not a place that you want to add complexity. It's error prone, it's really janky, it makes this code really hard to use for other projects and such. And this is often sufficient motivation to just like not want to use MiniHack. And even if you do all of this, it can be pretty slow. So we could also just do puffer PPO MiniHack. And now we're training MiniHack at high 3000s, close to 4,000 steps per second. So what did I change in order to make this happen? Did I just go make all of those changes and do it anyways? I added one wrapper. And it's not a MiniHack wrapper, it's a Gymnasium wrapper. A wrapper that will work for whatever Gymnasium environment, almost any that we support. Doesn't have to be added individually either. It's just, you know, a pretty good subset of Gymnasium M's that will soon be all of Gymnasium M. And then, yeah, there's one extra line with the agent creation function that'll go away in a moment. So how do we do all of this with one wrapper? How do we make this just work? I'm going to open up on the right-hand side this demo file. And we're going to run it on the left. Here we can see the observation space of MiniHack. It is a mess. You have a whole bunch of different elements in this dictionary. They're boxes with different shapes. They even have different data types. And now, if we look at what happens once we wrap it with Puffer, it is just about 13,000 uint8, so 13 kilobytes of flat data. Now, you might think that, sure, anybody can write a quick flatten wrapper. That's like 10 lines of code. No big deal. And that the problem with that is going to be that these 13,000 bytes aren't particularly useful because you need the structure of this when you go to run your data through a network. You're not just going to run your network on flat bytes like this. This is where the magic happens. And there isn't much magic at all. It's really just a Numpy feature that is a little bit lesser known. PufferLib infers this based on the observation space. This looks very similar, but this dictionary is special. This is a valid NumPy data type. This means that you can make a numpy.array with this data type, and NumPy is going to create something like a C struct for you. This is contiguous memory, and it can be viewed either as flat bytes or with this structure. So for demonstration purposes, this is the wrapped environment, so this is going to be 13 kilobytes of flat data. And we're just going to .view this data using this data type right here, this dictionary. And we can see that we recover the original data from the flattened form with all of the associated data types. And this is a view operation that does not have to copy. It is incredibly quick. This also works for vectorized data. So if I'm going to make a vec_env right here, we reset the environment to get the flat one, and then we're going to .view it to get the structured obs. This actually gives you batched data in the exact format that you would want it. 4 by 13 kilobytes goes to 4 by whatever the subtensor dimensions are. And this works for nested dictionaries, should work for tuples, works for lots of different data types. It's very general. Now, this is a very, very simple idea. It went through many, many iterations to get it to this. I didn't even know about the NumPy thing when I started making this, and I had my own custom implementations for a while. But it's incredibly powerful because it allows you to not have to care about structured data in your vectorization implementation, in CleanRL, or anywhere else other than in the environment itself and in the forward function of your model right before you need the data just in time. And there are going to be a little bit of additional detail required for that forward function, but really it's what you see here. So you can write your vectorization assuming that you have flat data, and it's going to work not just for Atari, but for anything. And you can write your CleanRL code. You can actually leave it exactly the way it is and run MiniHack. But making this assumption, you can optimize a whole bunch of things along the way. So not only is it going to be simpler, it's going to be way faster. I'm going to run the Puffer's vectorization. So same code with Puffer's vec. And now, instead of 4,000 steps per second, we're over 8,000. And the environment itself will run at over 50,000 with MiniHack because it has some slow wrappers, or at around 100,000 with NetHack. You're very much bottlenecked by the model here in CleanRL. But over 2x performance for a drop-in, and just to show you that it is a drop-in, that's all I changed. I swapped the vectorization. And as you can see, this annoying signature went away. So this is what I see is going to allow us to just move RL onto more complex and interesting environments and make it very easy to do so. But let's say that you're a researcher or a hobbyist working on something where you don't really need all these structured features just yet, and maybe you just want some speed ups on Atari or some classic environments, and then later on, if it's convenient, you'll think about moving to more complex and interesting M's. If it's convenient to do so, and if they're faster, and if it makes sense. Well, we actually have some speed ups even for the simplest case. So remember, we had 2,700 steps per second before with PPO Atari. That's still not a fair baseline to CleanRL because the batch size by default is just way too low. So we're going to just up the batch size from 8 to 48 to be fair to CleanRL here. And now we're going to get mid to high 4,000 steps per second. I believe when I checked this, it was 4,700. Okay, so 2,700 and 4,700. Now we're going to run Puffer's PPO Atari. Uses our vectorization. And it's a little bit faster. You're very heavily bottlenecked by the network here, since the batch size is so low. But, we already get a decent little increment. It scales a lot better, though. So if we run the large version, 4,700, we're going to get up to, if you can even read it, it's going so fast. If we let it even out, it will be right around 8,000 steps per second. 8,000 steps per second. So if we just look at the code change, This is the difference between the large Atari PPO and Puffers. The tiny little change. All I did was I added in Puffer's Vec, and I slightly changed the infos format just for convenience. That's all that's required to get this like 50-60% plus. It's actually close to double in this case. Performance improvement. We can go a lot farther than this. This is just what I wanted to show you exists with almost no code change required. The performance improvements are much larger for structured environments, for which Gymnasium and other standard VEC implementations are less optimized, or very often just don't work at all. So for the next set of demos, we're going to go into the main PufferLib repository. Max here is just 48 batch size. And this demo.py is just going to run our somewhat souped up version of CleanRL. I'll show you that there's no real additional magic to it in a bit. But for now, just it's CleanRL with additional logging and like one important additional feature. This is going to give us a nice dashboard as soon as it finishes making all the environments. You get this nice render in your terminal. And importantly, you get close to 16,000 training steps per second, another factor of 2. So from 4.7K all the way up to 16K, with minimal introduction of complexity, as I will demonstrate soon. Most of the additional code is going to actually just be for generating this dashboard and getting these detailed metrics and hardware utilization and all of that. But before we go into the nitty-gritty details where I demonstrate that to you for certain, let's take a look at what we can do with this simple little repository. We're going to run a simple environment that we can train quickly, like MiniGrid. We're going to specify multiprocessing. And we are going to set it as a baseline for WandB. I'm going to actually get out of this box and back to my laptop. I'm going to run the exact same container I have on the remote machine. And I'm going to go into here. We can see this is running at 40K steps per second, so by the time I finish typing this, it's already done running 1,000,000 train steps. Sync to WandB. Now I can pull that model down, eval it locally. I'm going to spawn on my other screen, so let me go grab the window. Here we have this agent that we just trained in 30 seconds on this desktop, running on my laptop, solving MiniGrid and rendering. Now, MiniGrid is a really simple environment, but the nice thing with Puffer is that this same sort of a workflow is going to work with just about anything. Let's run NetHack. I don't have a pre-trained model for everything, but I can at least run a random policy on it. And since this is ASCII, we can even render it on the terminal just with a little bit of flickering. So here we have NetHack running. For researchers on classic tasks, do breakout. Breakout runs. We actually include a few of our own environments here with PufferLib. They're very simple. This is, I actually have a baseline for this as well. This is a very simple test env. It's incredibly useful because you can train it in like 10 seconds and it will tell you 90% of the time that you've messed something up in your environment. Plus it'll render like this locally in a terminal. Just trying to get to the blue. And let's show just a couple more. Big fish seems appropriate for PufferLib. ProcGen has had some infra issues that needed some working around, but here we go. We've got breakout here. I realized that before when I dragged the window over, I might not have dragged it to where you could see it with my camera. But here you have big fish. ProcGen can run up from like 50,000 steps per second with the C++ bit vectorization. It's up now to 150,000 without needing C++ vectorization using PufferLib. That makes it a lot easier to work with and faster to boot. And the last one I'm going to show you is Neural MMO. Neural MMO doesn't have a local renderer, so I just wrote one very quickly so I could just show you that this will work for fancy multi-agent Ms as complicated as Neural MMO. Here you have in yellow all the agents running around, and in red all the NPCs. So now that I've shown you everything that is included in this demo, at least for training and inference, let me show you just how truly simple it is. There's a 300-line demo file, and our souped-up clean PufferL is 700 some odd lines. This is a total about 1,000-line demo, and as you're going to see, the vast majority of this is just devoted to all the profiling code and the dashboard. There's like 100 additional lines of actual code complexity added on top of CleanRL. Here's our init function. One screen of code, sets up the dashboard, sets up utilization, sets up an experience buffer, which is going to be the one additional thing, adds some features like torch compilation option, your optimizer, that's all. Here's your eval function. It is 75 lines of code. There are 2 or 3 main differences versus vanilla CleanRL. One is you have all of these decorators and contexts. This is purely to get accurate profiling for the dashboard, which is very useful in diagnosing how you can speed up your learning loop. The second major change is right here. This is data vec-env receive, and we have data vec-env right up here, send. This is an asynchronous environment API. Your algorithm is still PPO, it is still on policy. However, PufferLib introduces a Python implementation of envpool. Envpool is a project that allows you to run more environments than you need per batch, such that the ones that you don't currently have observations from are running in the background while your model is doing its forward pass. So you can drive your environment time down to 0, technically, if it only takes the time of your forward pass. This is where the other 2x performance improvement comes from, and the crucial thing with PufferLib is that it will work for just about any environment, compared to the original envpool project, which requires you to have bound C++ implementations for your environments. And it is very fast. Usually will give you a 2x improvement for most environments, unless your environment is really, really slow, in which case we've seen like 30-40% even then. So 75 lines for eval, including some additional junk that I need to get rid of. This is specific to a couple projects I'm working on. Train loop here is, I believe, around 150 or so lines. This is even more similar to original CleanRL. The main difference is here, the experience buffer, and then I Cythonized generalized advantage estimation, just because it was the bottleneck for really fast environments. Just for thoroughness, I'll show you that there is no magic here. This is your generalized advantage estimation. This is me adding some types, and now it's 20 to 50 times faster. Only makes a difference for really fast environments. Okay, so train loop. This is all from where we started before. This is all just standard CleanRL. This is Wanby integration. This is checkpointing. And there's the dashboard print right there. Absolutely no smoke and mirror. And then from here down, There's going to be the one experience buffer addition, which is 100 lines of code, and then the rest of this is just dashboard. I guess there's a little checkpoint as well. Dashboard. Okay, here's your experience buffer. It's 100 lines of code. This is actually a little bit complicated, but overall it's a pretty small amount of complexity to add for the amount of performance it gives, and it doesn't really mess with the APIs too much. What this thing has to do is allocate you a flat buffer of data so that when you store your data right here, you store the env ID and you store the step of that data. This tells you how to actually order your data when you're running training. And then when you sort the training data, it sorts the training data. And then it just reshapes it after it's been sorted so that all of the steps from the episode are contiguous. And it gives you your batches. That's all this thing does. 100 lines of code, a little bit of complexity, well worth it. The rest of this is all just checkpoint, and then one screen of code for the whole eval demo that I showed. All the rendering stuff is this one screen of code because PufferLib gives you a consistent environment for single and multi-agent. It makes everything behave really well. So as a result, like one line for ANSI environments, a couple lines for framed environments, one conditional for if the agent is recurrent or not, and that's all. Everything else is dashboard. This is all just rich printing of dashboard stuff. That is 700 some odd lines of the code. As for why the runner file is 300 lines, I wanted to make it really user-friendly, so I made the help menu dynamic. If you do breakout like that, it'll actually give you the policy args for breakout. It'll give you env args for breakout if there are any. So this is just computed based on your environment dynamically. That is most of the code in demo is just doing that. So here's your fancy config loader. It's a YAML file. You don't even need it. It's just for hyperparameters to make stuff easier. For generating the dashboard as well, there's some argparse stuff in here. Here's your make policy function, recurrent and not recurrent policies. Here's WANB integration. Here's sweeps integration for hyperparameter tuning with WANB. Here's your train function that selects if you want to run serially, multiprocessed, or with Ray. We have all of these. Ray is usually really slow, but it's good for multi-machine, I suppose, for really slow environments. And then we have vector make. Make your vecenv, your policy, and alternate between eval train, eval train, eval train. Everything else here is argparse shenanigans. So all the args that you can specify. Here is the WANB baseline thing. It literally is just uploading and downloading a PyTorch .pt. That's all that there is to this. Here's the call for the render demo. Here's the call for train. And then we have a couple other nice tools for you. Sweeps. Auto-tuning is fun. This is how you tell how to make your environment fast for your machine. This is a relatively new addition. .end batch. I believe it's train.end batch size. So this is going to find the best settings for your machine for breakout if you want a batch size of 24. And set like limitations on how much RAM and stuff you want it to consume. It'll just profile single core first, and then it will attempt to guess best settings, and it will evaluate a whole bunch of different settings. So these are all the tools that I currently have included with the demos for PufferLib. The library itself is very simple and restricted. It's mainly just, here's a wrapper to make all your environments behave nicely with whatever reinforcement learning you want. If you do that, then you can actually take the opportunity to make a whole bunch of optimizations to vectorization. So we'll go ahead and do that. And then all the demos are just very simple, built out of that, where those wrappers are doing the heavy lifting. There will be an archive manuscript as soon as the repository hits 300 stars, which could be in 2 minutes if you all wouldn't mind just starring PufferAI/PufferLib on GitHub. I'm working on this full time since I've graduated, so it really helps me out. I'd appreciate that. And that will include details of the vectorization and such implementation. Since I know I'm going to have questions on that, at a high level, the major optimizations in vectorization that make it this fast: hard assumption on PufferLib emulation, so you only handle flat data. Observations are allocated as big tensors in shared memory, so the workers will write directly into that shared memory without having to ever stack or concatenate data. We support multiple environments per process, so you don't crowd too many processes. The workers themselves, they don't rely on pipes for the most part or queues for sending data around. They actually busy wait on values in shared memory, which completely eliminates interprocess overhead because they're just waiting on a value to change that is not locked or anything. And infos are aggregated over episodes by default. That's one of the wrappers that we have. And we only will send the summed infos once per episode, and that's the only time that you have to pipe anything. That's to save like 40 microseconds or whatever, but it makes a big difference for fast environments. Those are all of the major optimizations. Beck, I'll be happy to take more technical questions on it or on the emulation, and I'll be happy to show code. But thank you very much. I really hope that this is going to be useful for everyone in RL. I hope this gets RL into way more hobbyist hands for doing cool projects that would have been previously hard. I hope that for researchers, this gets us looking at more complex and interesting environments by default. And I think that industry is going to find this a very useful simplification of very heavy tools that would normally be required as well. So thank you, and I'll take